Boiling point elevation is the extension of vapor pressure concept. Since we have normal boiling point at the standard pressure of 1 atm here, so we have the temperature for the normal boiling point is here. So when the non-volatile solute is added to a pure solvent, we are going to have a higher boiling point than the normal boiling point. The boiling point is increased or elevated when the non-volatile solute is added into a pure solvent, which inhibits the solvent from escaping. We can see that at the surface of the solution here, the presence of a non-volatile solute and fewer molecules of pure solvent at the surface, so the pure solvent cannot vaporize in this case. So the temperature must be raised so that the solution's vapor pressure must be equal to the atmospheric pressure, meaning that the vapor pressure is lowered according to the Raoult's law. And the amount of the temperature is elevated is determined by the number of moles of solute dissolved in the solution. Since we have boiling point elevation in this case, we also need to find the changes in the temperature of the boiling point. So we need to have a new formula here where the changes of temperature of the boiling point delta Tb equal to Tb minus T naught B. So Tb is the boiling point of the solution, which consists of the non-volatile solute, and T naught B is the normal boiling point of the pure solvent. So we can see that the Tb is greater than T naught B. So from this we can determine that the delta Tb is greater than 0. So in this case, we also have the formula here, delta Tb equal to Kb times M. What is Kb and M? M is the molality of the solution. In this case, molality is the relationship between the mole of solute per mass of solvent in kilogram. And Kb is the molar boiling point elevation constant for a given solvent. And when we get this delta Tb, we can also calculate the molar mass of the solute. When we get this value, we can substitute the value into this formula so that we can find the molar mass of a given solute. Let's take a look at an example here. For a 0.262 molar solution of sucrose in water, calculate the boiling point of the solution. So the boiling point of water is 100 degrees C and Kb is given as 0.512 degrees C per m. So what we need to do is that we have to calculate the boiling point elevation. We use this formula, delta Tb equal to Kb times m. So we have the information given, so we just need to substitute the value inside the formula so we can get the changes in temperature is 0.134 degrees C. And then next, we need to calculate the boiling point of the solution. Since we already have this value, so we can find this value. We also have the normal boiling point here, which is 100 degrees C. So we just need to substitute the value inside the formula. We can get the boiling point of the solution, Tb equal to 100.134 degrees C. Besides then the boiling point elevation, we also must consider the freezing point depressions. In this case, the normal freezing point at 1 atm is reduced when a non-volatile solute is added into the pure solvent. Freezing point is depressed when solute inhibits solvent from crystallizing. This is happen when solution freeze. The solid form is almost always pure, and the solid particle here does not fit into the crystal lattice of the solvent because of the differences in size. The solute essentially remains in the solution and blocks the solvent from fitting into the crystal lattice during the freezing process. So the differences from of the freezing point temperature is here we have Tf for solvent and Tf of the solution. So how to calculate the freezing point depression according to the Raoult's law? So here we have the changes in the freezing point temperature. So we need to have the formula where delta TF equal to T naught F minus TF. T naught F is the freezing point of the pure solvent. TF is the freezing point of the solution, which consists of the non-volatile solute. So from this formula, we can see that the T naught F is greater than TF and delta TF must be greater than 0. So the delta TF also using this formula, which is equal to Kf times M. M is the molality of the solution and Kf is the molar freezing point depression constant for a given solvent. When we get this, the delta TF value, we can calculate the molar mass of a solute by using this formula. An example here on how to calculate the freezing point depression. Determine the freezing point of a solution prepared by dissolving 500 grams of ethylene glycol in a 2500 grams of water, and the Kf for water is given here 1.86 degrees C kilogram per mole. So what we need to do first is we have to calculate the freezing point depression by using this formula, delta TF equal to Kf times M. But first we have to find the mole of ethylene glycol. So we already have the mass, so we have the molar mass. So the mass divided by the molar mass, we get the moles of the ethylene glycol. So we calculate the molality of solution by using the mole of the ethylene glycol that we get here earlier. So divide by the mass of the water, but we have to convert the gram to kilogram, and we can get the molality of the solution, which is 3.22. So from this, we can substitute the value inside this formula. So we can get the changes in temperature of the freezing point is 5.99 degrees C. Next is that we have to calculate the freezing point of the solution. By using this formula, we can get the freezing point of the solution is minus 5.99 degrees C. Please bear in mind that the normal freezing point of a solution is 0 degree C.